Right, if you will pull out the packet that we were looking at on Wednesday, I want to make sure you have the answers to these. So we did the concentration ones, the problems that you were, oh no, we didn't get to the second concentration. So we'll look at that one. But then the other ones were using atmospheres, but remember that pretty much works the same way. With this one, we've got a scenario where we don't have a 1 liter flask, we have a 10-liter flask. So what I would do is go ahead and put all of these in terms of molarity rather than in moles. If you leave it in moles, then when you get to plugging things into your equilibrium, you're going to have a bunch of 0.3 minus x over 10 and things like that. And this just kind of eliminates all of that fraction stuff that can be confusing. So what I'm going to do is I'm going to say if I have 0.30 moles of hydrogen, but it's in this 10 liter, I'm going to call that 0.030. And that's going to be capital M. So that's coming from this calculation. Okay. And then I'm going to have the same thing for the iodine. I probably should have written a little bit smaller, but I'll have 0.030 here. I don't have anything at the beginning here. My change is minus x plus 2x. And then my equilibrium is just summing up these columns. So this is 2x. This is 0.030 minus x, and this is 0.030 minus x. And then we're given the constant here. So what we want to do, we don't have anything that we have both a number and an x value for. So what we're going to have to do is plug all of this into the equilibrium constant expression. So that expression is going to be based on this. All of these are gases, so they all get included. So Kc is going to be the concentration of the product. And this gets squared because of this coefficient divided by the reactants. Now we don't want to put in our initial concentrations because this is only true at equilibrium. And if we put it in the initial, we would have 0. And that's not a true statement. So we're going to plug in this stuff, which unfortunately has some x's that we're going to have to solve. So we're going to have 2x squared over 0.030 minus x, but we're going to multiply that by itself. So that's the same thing as saying that whole thing squared. And that's important because that's going to help us in solving this. So this is equal to this 45. All right. And then since both of these are squared top and bottom, we can just take the square root of the whole thing. And we don't have to worry about polynomials. We'll just have simplified x. So I'm just going to square root everything here. So that's going to give me, let's see, on top, I'm going to have square root of 2. Oh, wait, I'm sorry. This was supposed to be in parentheses. I was getting lost. So we're going to have 2x over 0.030 minus x equals 45. Okay, and then, oops, slide that so that you can see it. And then it's just a matter of rearranging things until you can solve for your x. Just remember that once you solve for that x is going to end up being not your final answer, but the equilibrium concentrations. Yes, that should be the square root of 45. You're right. Which I think is 13 point something, and I'm going to have to plug that in. I'm trying to remember from yesterday. I can't do square roots in my head. 45. Oh, no, 6.7. All right. So when you end up rearranging all of this, I believe that x turns out to be 0.0021. So I encourage you to do that solving. Make sure you come up with the same number. And then whenever we get to x, we go back to the question and say, does that answer the question? Well, it says, what are the equilibrium concentrations of these gases? None of these is in equilibrium, or none of these is equal to x. So we're going to have to plug it in and say for HI, this is gonna end up being 0042. And then 0.028 and 0.028. Oh, that's okay. And then you can always double check that by plugging these numbers back in. And if you end up getting 45 when you plug it in, then you did a good job. Okay. For the next one, they didn't give us an equation. So if you were trying this one and you're like, oh my gosh, where's the equation? Well, you're gonna have to come up with this. So it says we put nitrogen dioxide into the flask. So that's the reactant. And then after some time, it dimerizes. So dimerizes means we just put two together, but you know, you can see the formula there. So we can say, okay, it's going to form N2O4. Got to have that balance. So there's going to be a 2 here. All right. And you're going to go through your ICE table. You got 1.00, 0, minus X, minus 2X plus X. 1.00 minus 2X, X over here. And you're going to end up with, because this also gives us the K, you're going to end up with X over 1.00 minus 2X squared. Now, in this case, we can't avoid the polynomial. So you are going to end up having a quadratic formula that you're going to have to work out. So remember, to do the quadratic formula, you want 0 on one side and everything else on the other side so that you have A, B, and C. And so what I get for that is negative 6.66x squared plus 14.3x minus 3.33 equals 0. Okay. So this is A, don't forget the negative. This is B, and this is C, don't forget the negative. Okay. You might have on your, if you have a graphing calculator, you might have something that can find the roots for you. Since I'm not going to ask you to use the quadratic formula, I'm okay with you doing that, but keep in mind that if you're planning on taking an MCAT, a PCAT, a DAT sometime in your life, knowing how to solve the quadratic formula is a good idea. So if you plug this into the quadratic formula, remember that's going to give you two different answers because you have the B plus the square root thing and the B minus the square root thing. So this is going to be, our two choices come down to 0.266 or 1.9. Now, if one of these were negative, we could say, well, that doesn't make sense. We can't have a negative concentration, so that can't be it. So what can we do to figure out which one of these is the real concentration? Or the real X rather. What's something else that wouldn't make sense? Say again? Plug it. So you can plug it in to try and figure it out. So let's say I plug in this 1.9 up here where we have 1 minus 2 times 1.9. Now I'm going to have a negative number, right? So this one doesn't make sense because it's going to end up, when I plug it in, give me a negative number, okay? So this is our value of X, and then we use that to plug in the other concentrations, okay? Let's see. On this one, we had 1.00, 0 and 0. So remember, if it doesn't tell you a concentration, you're going to put 0 for initial, and that's often the case for our products. Our X's get the same coefficients that the equation had. So this is 2X plus 2X. This one is plus X. And then here we have 1 minus 2X, 2X, and X. Now I dropped my sig figs here, but I have to remember when I'm doing all my calculations that there's actually a couple of zeros there. So let's see, what are we told? We're told 2.1% of the molecules decompose. So I have 1 here, and I know that 2.1% of that decomposes. So 2x is equal to 0.021. And x is equal to 0.0105. That makes sense? So then I can just plug in those values here. This one's going to be 0.021. This one's going to be 0.0105. And this is going to be 1 minus that 0.021, or 0.98. And now I have equilibrium values that I can plug in to my K expression. And I will let you try that. I get 4.83 times 10 to the minus 6. Okay, so notice we have sometimes this is a negative exponent, sometimes it's a large positive exponent. K can have a real range on it. All right, and then on our last one here, we've got a solid. So the solid is not part of the equilibrium expression. That simplifies things for us. There's no division. Okay. We are told that the total equilibrium pressure is 4.3. And let's see, sampled solid is put in there. So we start off with 0. Okay, so this is going to end up being plus x and plus 2x. So x and 2x. Okay, the pressure is coming from all of this. So x plus 2x is equal to 4.30. Right, so from there you can solve for x. I get x is equal to 1.43. And then you plug that into your expression for Kp. Remember, Kp only has our products. N2O, I'm sorry, these are pressures. Pressure of N2O and pressure of H2O squared. And this is multiplying, not adding these. So when I plug that in, I get 11.7. Oops, not on the screen. Okay, so I didn't do math-wise step by step for you. I encourage you to do that to get the practice, make sure that you can follow along, because I know a lot of you, the problems you had with the rate law problems were rearranging algebraically. So check to make sure you're knowing how to do that. Any questions on those? All right, so those are probably, especially the ones with the quadratics and the squares in it, that's trickier than I would give you on a test, because it just takes too much time, and I'd rather ask you more quicker questions to find out breadth of knowledge than to have you gain or lose all your points on just one problem.